Welcome to CP 329 Serial Peripheral Interface lecture. The Serial Peripheral Interface is a serial communication protocol that is quite popular. It features fast data transfers synchronized on a clock signal. So of course that means that we are transmitting a clock from one device to another. So in many microcontrollers we'll have an SPIs. The serial interface, we transfer 1 bit per clock edge. And it's because it has a clock, it is synchronous. The clock's role is to indicate when a data bit is being sent and when it can be read. The clock frequencies of the SPI can range between 1 and 100 megahertz, at least I've seen commercially. And so that means approximately you could get about 100 megabits per second data rate with this protocol, but practically speaking, probably far less than that. The SPI operation is what they call a master-slave protocol. Sounds awful, but that's the nomenclature in the field. So SPI master is the one who drives the clock, so it provides the clock to synchronize all data transfers. And if the clock is not present, that means there's no data being transferred at all. So when you're not transferring any data, it doesn't have to send out a clock all the time. The master also controls a slave select signal, which is basically like a chip select signal that allows it to select multiple different slaves all at the same time, or one at a time, or however it activates them. So data using SPI, data can be exchanged between the devices, between the master and the slave, and in both directions. And so the way that's accomplished is as data is being clocked out, data can also be clocked in. So the slave will see that the clock is happening, and it will send out data bits synchronized to that clock. A data bit is sent out at the rising or falling edge of the clock, depending on how you configure your SPI. Now there are 4 wires in SPI that make this protocol work. There's the serial clock line, which of course has the clock on it, and there's a slave select. You may need more than one slave select if you have multiple slaves out there. And typically this signal is active low, so it idles high, and then once the master wants to select a slave, it pulls this line low. Then there is the master out slave in, MOSI, or also sometimes called serial data out. So as the name says, this is where the master's output is, and this is where a slave is reading from the master. Likewise, there's also MISO, master in, slave out, where the slave is writing out and the master is reading, and this is sometimes called SDI, depending on the device you look at. And so, quite simply, if you had a master slave like this, we would have, here's the master, and the master is going to generate the clocks, and it's also going to assert the slave selects. When the slave select goes low, a clock will be generated, and at the same time, the master here can put data into a shift register, and 1 bit of this data word or data byte could be shifted out at a time. Likewise, the slave can send out data to the master that way. So typically, I've seen this almost exclusively. The slave selects are only asserted once per byte, and so you transmit 8 bits at a time. But that's maybe not necessarily true, but that's what I've seen in all my experiences with microcontrollers. The SPI data exchange, again, here, this is what the 4 wave lines would look like. Here I show S clocks, slave select, again, active low, slave data out, which is also MOSI, serial data out, sorry, which is also MOSI, and then SDI, serial data in, which is MISO, which and apparently the slave here is not transmitting anything. And so here we see, okay, the most significant bit gets transferred first, and and the slave here knows to read it on this, I guess it's this falling edge of this clock here. I don't know why the arrow's backwards. And then goes on to the next bit, next bit, next bit, next bit. Once all 8 bits have been transmitted, the slave select goes back high, and notice the clock stops too. Okay. So whether or not the data is being read on the falling or the rising edge is a configuration in most SPI systems, and as well as whether or not the clock idles high or low. So the clock polarity setting in SPI determines whether or not the clock idles high or low, and the clock edge select determines whether or not the data is on the first edge or the second edge. Now I'm saying first edge and second edge because the first edge could be rising or falling depending on how the clock idles. And hopefully if you don't understand that, I encourage you just to draw out some waveforms of whether or not the clock idles high or low. It's pretty simple. Okay, so quite quickly, I'm just going to talk very briefly about the AT mega SPI. You're going to do an exercise on this anyhow. There are 3 control registers for the SPI. So this is very similar to your timers or GPIOs. There's the serial peripheral interface control register, SPCR, and this enables the SPI. Allows you to have interrupts where you could generate an interrupt once the byte is transmitted or once you've received a byte. Can set the polarity and phase as we talked about in the previous slide, as well as the data ordering, whether or not the most significant or the least significant bit gets sent first. This SPI status register, SPSR, tells you whether or not your SPI FIFO is empty or full. So basically when you put a byte into a register, it's going to get shifted out 1 bit out of a time, and it could give the status register could tell you, okay, I'm finished transmitting that byte, or I'm finished receiving a byte. And then you've got to put the data somewhere, and so this is the data register that the data gets shifted in and out of, and this is the SPI data register. So, of course, I would like for you to read the data sheet in this respect. There is an app note that's pretty handy if you with some code examples, and also there's our tutorial on Polylearn, which you have to do as part of this course. So thanks.